Welcome back, AP. Calorimetry is probably the biggest topic that is in this chapter. Not only is it calorimetry a huge topic, but the lab that goes with it. Okay, so as you can see, we got a lot of learning objectives, and let's go through each one so we know what AP expects us to know. Calculate heat that's either absorbed or released by a system undergoing either heating or cooling based on the amount. So we're going to talk about mass and something called heat capacity and change in temperature. So we got delta T, we got mass coming in, and this thing called heat capacity. So in this one learning objective, we have 6 subtopics that we have to talk about. The heating of a cool body by a warmer body is important in the form of energy transfer. So remember, this is how we have to know if energy is going in or is energy coming out. The amount of heat transferred between two bodies may be quantified, so which means we're doing math, okay, by the heat transfer called Q equals MC delta T. Now we're going to be using this equation quite a bit, so let's get out a calculator too. I'll go over the specifics of each part of it when we get further into the notes. Calorimetry experiments are used to measure heat transfer, okay? So we got to know, is heat coming in or is heat coming out? So that's the purpose of calorimetry. That's how we can measure it. The first law of thermodynamics, which we know that first law by now, is that energy is either energy is conserved in a physical or chemical process. So remember, you can't gain or lose, but you can transfer, but it has to be constant in the end. The transfer of a given amount of thermal energy will not produce the same temperature change in equal masses of matter with differing specific heat capacities. Now, this is a big one because if the chemical is different, no matter if you have the same masses, you won't get the same change in temperature because of something called specific heat. So we will go through that one too. That one's a big one though. Heating a system increases the energy of the system, while cooling a system decreases the energy of the system. Pretty self-explanatory right there. The specific heat capacity of a substance and its molar heat capacity are both used in energy calculations. All right, so we got to know about those calculations. Chemical systems change their energy through 3 main processes. So heating and cooling, phase transitions, and chemical reactions. This one, phase changes, we talked about this in Intermolecular Forces, Chapter 11. Heating and cooling, we are going to talk about that some more in here at the lab. But then what happens if it's a chemical reaction? So we're going to get into those 3. Learning objective number 2, calculate the heat that's absorbed or released by a system undergoing a chemical reaction in relations to the amount, so we got mass again, the reactant substance in moles and something called molar enthalpy of reaction. So delta H, sometimes you're going to see the word mole or molar. That just means we need moles instead of grams. The enthalpy change of reaction gives the amount of heat energy that's either released, so we're going to have negative values, or is it absorbed, as in positive values. But because of calorimetry, we need constant pressure. We need that constant pressure so that way we know Q equals that delta H. So we got a lot that was mentioned in here, but now let's go through it one by one. First thing is, what is heat capacity and what is specific heat? You heard it up here. You heard them talking about heat capacity, and you also heard it right here, specific heat. Well, first of all, what are those 2 things and why is it important? So here, definition, heat capacity measures how much heat a whole object can absorb. So like a pot versus a spoon. So if you actually heated up a pot versus a spoon, which one's going to get hot faster? Well, that spoon is, and the reason why, because of size and mass. So specific heat tells us how much heat per unit of mass a material can hold, as in water versus iron. So this is all about the material and mass. Okay. Specific heat is more about the material, water versus iron. Okay. So it's completely different. This one's more about mass, aka size. Okay. What if they're both aluminum, but one's an aluminum pot, one's an aluminum spoon? There is a difference. So, key to this is huge. Okay. Highlight that bad boy. Box it, highlight it, put stars and circles and all this neat things around it. Specific heat and heat capacity are not the same thing. So I gave you a couple analogies. Think of like heat capacity is the total storage space of the fridge. I mean, it's the whole fridge. So if I have my refrigerator, I got my door, got my little handle right here. Okay. Heat capacity is the whole thing. That's heat capacity. Okay. Specific heat is how efficient it is at cools each liter of liquid. So when you open it inside and you got your container of milk or your container of water, that's specific heat. It's how much heat or how efficiently it cools that specific chemical, that 1 liter of chemical. So that is specific heat. I gave you another analogy with like cereal. Specific heat is if you were actually bargain shopping out there, you know prices are crazy right now. Don't get me even started about grocery shopping. Specific heat is the price per gram of that cereal product. So like if that box of cereal, so this box of cereal says it's $3 per gram. Okay, that would be kind of a lot. Okay, because most of the time the boxes are in most of the stuff we weigh stuff in ounces and pounds. Heat capacity is the total cost of that box of cereal. So if this box of cereal has a total of 10 grams and it says it's $3 per gram, well, that means the total cost would be 30 bucks. Now, you know nobody's out there spending $30 on cereal. Heck to the no. Okay? No way, no way. But that's the difference. This one's specific heat versus heat capacity. Okay? And specific heat and heat capacity do have abbreviations. We'll get to that on this next page. The key to this is specific heat and heat capacity. They are not the same thing. Okay? So I even have a comparison table for you in case you still haven't got it. So let's get a little bit more deeper. There are two fundamental concepts of thermodynamics, and they describe how materials interact with heat. While they sound they sound similar, they measure different aspects of thermal energy absorption. So we're going to go through each one. So definition is heat capacity, the total heat required to raise the temperature, so increase that temperature, but of the entire object, okay? Like the entire spoon or the entire pan. I'm just trying to raise it 1 degree. That's all I'm trying to do. Specific heat is the heat required to raise the temperature of just 1 gram of a substance, okay? So maybe that box of cereal, if it's 10 grams, I'm just trying to raise 1 gram. So it's not the whole thing, it's a part of that thing. The units are different. We've already talked about joules. For units, you can either joules per Celsius or joules per Kelvin. For specific heat, we actually need to know the mass. So we need joules per grams degrees Celsius or joules kilograms degrees Celsius. We're only sticking with the grams. We don't usually do kilograms, okay? This also could be joules over grams times Kelvin. Do not put a degree sign by Kelvin. Remember, Kelvin is a calculation, not a thermometer. So you could either do that one too, okay? There is a beware. Beware of temperature. Okay. When you have Celsius versus Kelvin, and I'm going to put it down here. I know I'm going to talk about it later again. When you have 1 degree Celsius, if I add 273 to get it to Kelvin, it's 274. If I go 2 degrees Celsius, add 273, I'm going to get 275. Okay? When you have thermal chemistry, thermodynamics, do not add 273, okay, to get to Kelvin. The reason why is for every degree that you increase for Celsius, you also increase 1 Kelvin of that same degree. Okay, so there's no reason why you have to add 273 to it. So the point is, you can use Celsius or you can use Kelvin, but do not add 273 to it. And I'll show you in the math why. The equations, heat capacity is big C. Big C. You take the mass times something called specific heat. Well, notice that heat capacity is big C, specific heat is little c. I would have called it little s if I was, coming up with this, but that's, I'm not the famous scientist that did it. So be very careful with this capital C versus lowercase c. So this is heat capacity and this is specific heat. Whereas specific heat, to find heat, I'm looking at mass, which is grams. Specific heat, which we just said right here, specific heat has to be joules, grams times Celsius. And then you have change in temperature. So remember, change in temperature is final minus initial. So final minus initial, you're still going to get the same unit. You're still going to get degrees Celsius. Now remember I said you can use Kelvin too. The Celsius will cancel, my gram will cancel, and then I get joules in the end. Okay? Specific heat, little c, has 3 units, whereas heat capacity only has 2 units. Okay? An example of this would be like if I was measuring 2 grams of iron, that has a higher heat capacity than 1 gram of iron. Okay? Because the mass is different, but you have the same material. Okay? Whereas this one is water has a specific heat of 4.18. He has one of the highest specific heats, as you see right here. Water. And this is a value to know. We got to know water specific heat. Whereas iron has a specific heat of 0.45. Much, much lower specific heat. So this one would actually be the same mass, but different chemical. So you're seeing the difference. Probably coming to you. You just need some more examples, okay? In practical uses in life, a large copper pot, a lot of people, when they buy their pots and pans, they like copper pots because copper can actually hold more heat. Whereas aluminum, not so much, okay? So these two, notice it says a small aluminum spoon because it contains more material. The copper contains more material, so it can hold more heat. Okay, even though we compare different chemicals, this one has to do with size. Okay, whereas water has a high specific heat, meaning it can take in a lot of energy to warm it up. This is why oceans regulate Earth's climate, and that's why when you go into an ocean, it's a lot more colder than it is than like a bath water, okay, because the sizes are different. So why does this matter in real life? Well, we actually use this in real life. It's just no one's talking about specific heat and heat capacity when they're cooking or climate change or heck, even your cars. So I gave you some real life example. Why do some pots of pans get hotter faster than others? So like aluminum, thin aluminum pan, it heats up quickly because aluminum has a low heat capacity. It doesn't store as much heat. So that's the purpose of heat capacity. It's about how much heat can it store. Whereas, or however, its specific heat is also low, meaning that it loses heat quickly too. So when we compare specific heat and heat capacity, depending on the value, is it storing a lot of heat or is it releasing heat much quicker? A thick iron cast. I know I love my iron skillet that I have at home. I use that more than like aluminum pots and pans because it can hold more heat because it's very heavy and it retains heat longer. Its specific heat is low, which means it doesn't warm up as fast. Okay, if you ever have like a comal, like a cast iron, either pan or comal, you'll notice that when you turn the stove on, it's not instantly hot. You have to wait for that comal to actually absorb that heat. So then it'll warm up your food, but it takes some time because its specific heat is very low. So it doesn't warm up as fast as aluminum does. Water, as we said, has the highest specific heat. It stays hot for longer. That's why when you guys put like ice cubes in your thermoses, your insulated containers, that ice is still ice like by the end of the day. Or if you put like hot liquid, like hot cocoa in a thermos, an insulated cup, it's hot at the end of the day too. Okay, because remember, insulated cup, this is a closed system. Okay. Oceans have a huge heat capacity. So when the sun shines down on the water is because it's massive and it contains trillions and trillions of liters of water. Remember, this is about size. Their high specific heat means that they absorb and release heat slowly, moderately throughout whatever coastal climates that it's in. Even in cars, radiators are designed with materials that balance heat capacity, the amount of heat to absorb that heat energy. That's why your car engine doesn't like overheat like every day because of heat capacity. Specific heat to release it more efficiently. So that's why you guys add like radiator fluid, antifreeze, because you're trying to keep your engine cool where it doesn't overheat. Now, common misconception, more heat capacity means better at holding heat. No, 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 not always. A material with very high heat capacity, like a thick brick wall, can store heat but may not transfer it efficiently. So because it has a high heat capacity, it can store a lot of heat. And I'm going to do my little triangle for heat. For cooking, you'd want a material to balance the heat capacity and the thermal conductivity. So that's why we use cast iron, we use stainless steel, we use copper pans, aluminum not so much because aluminum doesn't hold as much heat as like a cast iron. Water has the highest specific heat of all metals, okay? And as we said, we're going to know that value, okay? Beyond true. Water's heat capacity is high because it's used in central heating systems and thermostats. When substances like ammonia or glycerol have lower heat capacity, making water the gold standard of heat storage, okay? That's why we use water to boil and make our food, because of how much heat it can hold, okay? When we do calculations in about 10 seconds, we're gonna need these values. These are common materials and their specific heats. As you know, water's right there. Water has a specific heat of 4.184 joules, grams, times degrees Celsius, or as I said, joules, grams, times Kelvin, okay? Out of all the liquids, it's got the highest specific heat for liquids. Some metals out there, as you see, glass, we got air at constant pressure, okay? So these are common specific heats. So we're going to calculate. Let's bust out those calculators. Let me get mine too. How do you calculate the difference of them? So to calculate the heat capacity or specific heat step by step. Number one, measure the mass of your object. Okay, so in this case, I said if I have 50 grams of iron, measure the specific heat. Well, most of the time, it gives me the specific heat. So for iron, I just look up here, 0.45 joules grams over Celsius, which I wrote right there. Simple formula. So heat capacity, the mass times specific heat. So the mass is 500 of iron, and I'm going to multiply it by the specific heat of iron, 0.45 joules grams degrees Celsius. Simple multiplying. So I'm going to take that 500 times 0.45. It looks like only 2 sig figs. So I'm going to go, the calculator says 225. I'm going to, excuse me, I'm actually going to go scientific, 2.2 to the second, or I could say 220. I know it's a 5. You can even say 230. Okay, either one of those ranges. The only thing that cancels is the grams. So I'm going to have joules degrees Celsius. Okay, and notice these values, always positive. Okay, because specific heat values are always positive. Now, this equation, not on equation sheet. So it's one of these. Let's learn it. Okay, let's learn that specific heat. This is the device that we use to measure the heat transfer. It's called a calorimeter. So calorimetry, first of all, the definition is the measure of heat flow. Is it going in the system or is it coming out of the system? Okay. Calorimeter, that's the device. That's the apparatus. Okay. So this is what the actual setup looks like. AKA, we call it the coffee cup calorimeter. It measures the heat flow. So there's a couple things that you need with this. You need styrofoam cups, okay? And we usually use 2 of them, and we call them nested together. They're just stacked on top of each other. You have your water. As of right now, you have your water, okay? You have your thermometer sitting in there. And then the very first thing we're going to do is we're going to put a piece of metal. Now, it can be a chemical reaction, but the first thing is we're going to say a piece of metal. Now, your system is the reactants and the products. So in this case, our system is the metal, okay? The surroundings is everything else. The water, the thermometer, the cups, your hand, so forth, so forth. But we want to keep this under constant pressure because that way we know delta H equals QP. So we have an equation of calculating specific heat. So we got to know the mass, we got to know grams. We got to know who the chemical is so we can look up its specific heat. Notice it's little c. So joules, grams, degrees Celsius. And then we got to know delta T. We got to know the final temperature minus the initial temperature. So this temperature, when we subtract it, I'm still going to get degrees Celsius. So notice the difference with heat capacity. My Celsius cancels and my grams cancel. So all I have left is joules. Where when we looked up here for heat capacity, we have joules per degree Celsius. So the mass is canceled only, not the temperature. Okay. As you see on your equation sheet, it's right there. And they even give you a little color code key right here. So that way you know what is what. So you have this one, but you don't have heat capacity. Okay. So let's practice this one. A piece of iron, and I have a mass, 135 grams, is heated from, there's my initial temperature, 100 to 350. It's a final. Calculate how much heat, so I'm looking for Q and I'm looking for joules, is required. I always like to do my delta T first. So my delta T final minus initial. Okay. So 350 minus 100, so 250, but I'm going to keep proper sig figs. And then because I know the mass, I know who the chemical is, and I know how temperature change, I'm using specific heat. So mass times specific heat times delta T, okay? When we did the equation above, we didn't know how temperature changed, okay? We knew the mass and we knew who the chemical was, but we didn't know temperature. So see how the difference is, okay? So I know the mass is 135 grams, and this is of iron. According to my specific heat chart, I gotta go look it up because we're not memorizing iron, 0.45. And that's joules, grams, Celsius. I already calculated my delta T, so 250. And everything will cancel except those joules, and simply just multiplying. So I get 135 times 0.45 times 250. Keeping 2 sig figs, this is a big number. So you could say 15,000 joules, or you could say 1.5 times 10 to the 4th joules. Okay, either one is fine. You don't have to say both of them. That would be overkill. Okay, let's try another example. Whereas this time, what if we want to calculate specific heat instead, which means I'm looking for little c? Well, you have this equation on your equation sheet. But can you rearrange the equation? Can you solve for specific heat? Absolutely. Just take specific heat and move the mass and the delta T down below. Easy peasy, okay? You know AP is not going to give you every equation, so it's called proper algebra. Make sure you know how to rearrange an equation. I have 427.5 joules of heat. I know the mass. I know that copper went from 35 to 65, and I'm finding specific heat. So let's take care of our delta T first. So 65 minus 35. So that looks like 30. Now I'm going to put a decimal there because I had 2 sig figs. I need to keep the 2 sig figs going. So then, because I know specific heat, I can rearrange an equation myself. I have specific heat, and they put that little P there. That means just constant pressure. Okay, that's all that means. So then I have Q over M times, and you do the little dot, or you can put the little X, delta T. My Q was 427.5. My mass was 75 grams. And my delta T was 30. Okay. So notice none of the units cancel. And it doesn't cancel. Okay. Because remember, we're looking for a specific heat. So to plug this in, some people like to multiply the bottom and then take 427 and then divide that. Nothing wrong with that. Okay. I like to hit 427.5 and then hit divide 75. And then I get an answer. And then because the 30 is in the denominator, you're dividing again. So the question is, how do you want to plug in your calculator that makes sense to you? So practice right now. If you get the answer 0.19 joules, grams times degrees Celsius, then you did it right. Okay. Now another unit that we use besides joules in AP is something called a calorie. Now be very careful. This is not food calories. This is energy calorie. So how does that correlate to the food calorie? Okay. So 1,000 energy calories, we call it little cal, is 1 food calorie. So when you look on the back of whatever food or your drink you're consuming and it says 200 calories, well, energy calories versus 200 food calories. So if it was 200 food calories, Then you take 200 times that 1,000 and you get 200,000 calorie of energy that you would need to burn it off. Okay. Well, we're not doing any of those kind of calculations, but we are using energy calorie as in little cal. So notice how this number, 4.184 joules, equals a little cal. Doesn't that seem like a very, I don't know, knowledgeable number? Because we know that is water's specific heat value also. Ding, ding, ding. Hint, hint, hint. Okay. This is a value that we need to know because it's not on our equation sheet. So 1 little cal, 4.184 joules. What if I want to take my answer from number 2 and I want to just convert it to calories? Well, I need to go back to my answer for number 2, which was 15,000 joules. And if I just want to go to calories, I'm just doing a simple conversion. Joules on the bottom, 4.184 joules. And then 1 little cal. Make sure the cal is little c. Okay, bye-bye joules. And then simply divide. It's not a hard conversion. So 15,000 divide 4.184. And you get with 2 sig figs about 3,600 little cal. If AP asks you go to kcal, okay, which is kilocalorie, so kcal, or the rock station if you're into that, okay. Calories can also, just like joules, be in the box. So kilo, hecto, deca, and then joules, okay, or as we just said, calorie can be in the box too. So if I have calorie going to kilocalorie, so I just go 1, 2, 3, move the decimal 1, 2, 3, which also becomes 3.6 kcal. Okay. If they just ask for calorie, then that's fine. I just want you to see that kcal can also be moved along with King Henry, moving that decimal along. All right, let's look at some sample AP type questions, okay? Learning objective 2.C. Explain the relationship between transfer of thermal energy and molecular collisions, okay? So we're looking how energy and the molecules move to create that energy. So particles in a warmer body have greater kinetic energy, and we know this from gas laws. We know if the temperature increases, we have more energy, and not just energy, but moving energy, okay, especially for warmer bodies. So for warmer or hotter temperatures, we crank up the temperature, we got more energy. Collisions between particles in thermal contact can result in the transfer of energy. This process is called heat transfer or heat exchange or transfer of energy as heat, okay? And we know that the more collisions you have, the more heat transfer or energy transfer you have. So increasing collisions also increases energy. Eventually, thermal equilibrium, okay, is reached. So equilibrium is reached as the particles continue to collide. So remember, collisions don't ever stop. The reaction may have stopped, but the collisions still keep going. At thermal equilibrium, the average kinetic energy of both bodies is the same. Hence, their temperatures are the same. And we also talked about this in chapter 10. Okay, so this is great review of chapter 10. If the kinetic energy stays constant, then that means the temperature stayed constant. You can't have one go up and the other one not do the same. Okay, so we have a couple AP type of problems where my good friend Mr. Fairbraw did some lab scenarios to help you with this around approximately 22 minutes. I'm going to do this one with you, but if you need a little bit more love from Mr. Fairbraw, please just copy and paste this title right here into YouTube. Fast forward to about 22 minutes, and then you'll get some assistance. Okay. So with calorimetry, what if we take cold water and we put a hot object in? Okay. Well, we know the cold water has very low temperature and the hot one has very high temperature. Okay. As soon as that hot water, as soon as that hot metal hits it, and remember this is a piece of metal, we're going to start with the metals first. That hot metal is going to be releasing heat into the system. Well, that means the water's temperature will increase, and that's why you see the word cool. As the metal's temperature decreases. I didn't say negative, I just said decrease. Okay? Eventually, you will hit what's called thermal equilibrium, whereas it says right here, when the temperatures are both the same, the kinetic energy is the same. So now, eventually, at some point in time, the temperature will remain constant. And when it remains constant, that means these two will be at the same temperature. Okay, so it's not giving up any more heat to the water, and the water's not absorbing any more heat. It has reached thermal equilibrium. So one factor that we always need to remember is that heat always flows from hot to cold. When two substances, metal versus water, at different temperatures, okay, so this is initially, come into contact, the higher temperature, aka the metal, will start to lose energy, aka heat. And the lower temperature, water, will start to gain it. Okay, so the metal will start to lose it as the water tends to gain it. Heat is transferred always from hot to cold. The atoms of the metal start to slow down, so they lose kinetic energy because the water is gaining that kinetic energy. The lower temperature water will gain that energy from the higher temperature metal. So remember, the metal's still losing it. The water molecules gain energy and increase their speed. It's because the temperature increased, they have gained kinetic energy, which means they're faster. And not only faster, but more collisions. So the amount of energy lost will equal the amount of energy gained. So that energy that the metal lost will equal the energy that the water gained. And this should sound very familiar to you. It's called the first law of thermodynamics. Energy is not created or destroyed, it just got rearranged. So whatever was lost is also gained. So you can even apply this to heat. I know I put Q's up there. It's because we're getting ready to calculate some Q's. So eventually the system reaches thermal equilibrium, in which each substance has the same kinetic energy because they have the same temperature. So when the temperatures stay the same, you have the same energy for the metal and the water. So when we do calorimetry in AP, we do it two different ways. Number one, first lab, we're going to take a piece of metal and we're just going to put it in water. Okay. So in this scenario, you have a sample of copper metal is placed in bath water of boiling water of 100 degrees. So there's 100 degrees because it does say boiling. Okay, we're taking that liquid and changing it into vapor. The hot sample of copper is quickly removed from the water bath and placed in a sample of cool water. So this right here, this cool water is at 20 degrees Celsius in that styrofoam cup. So this hot piece of metal, so I'm going to say copper, this copper right here, it gained the energy from water and it got heated up. So all of that heat from water went straight into the copper. So that right there at boiling, the temperature of the water is equal to the temperature of the copper at boiling. So that means if both of them are at 100 degrees Celsius, okay, that means initially T initial is 100 degrees. And then I put in the piece of metal, and then the water was that, and I'm going to put right here, water was 20 degrees. Well, you know what's going to happen. That hot metal, this copper, is spewing out all that heat. So this initial water that was 20 degrees Celsius is finally, this water is going to be higher than 20 degrees Celsius. Okay. For copper, initially, because remember, it absorbed all that hot water, initially it was at 100 degrees Celsius. But as soon as you put it in this cold water, it's releasing all this heat. This final temperature is going to be lower than 100 degrees. So heat is transferred from the hot metal to the cool water. The atoms of the metal slow down. The molecules of the water speed up because you gave it energy, you gave it heat. Eventually the system will reach thermal equilibrium, in which case each substance has the same kinetic energy because it has the same temperature. So the key to this lab is when you watch that thermometer and the temperature stops changing, that means you have reached thermal equilibrium. So that means the temperature of the metal is going to be the same temperature, and I'm just going to say warm water, okay? Not hot water, warm water. So I gave you a scenario, okay? Let's say we started with a piece of metal that was 50 grams. Initially, the temperature of the copper was 100. The mass of the water was 100. The initial temperature of the water, now this is the cold water, is 20 degrees. And then once you put the copper into the cold water, you then got a final temperature of 23.6. So remember, this is when you took that piece of metal and you dropped it in that cold water. So that right there, that is your final temperature. So remember, we call this thermal equilibrium. Okay? So what are some sample calculations that you could be asked? What's the delta T for the copper? Well, it's final minus initial. The temperature of copper started at 100 and it went to 23. So when I subtract this and proper sig figs, 23.6 minus 100 should make sense. I lost 76.4 degrees. Right? I lost heat. That should make sense. My temperature went down. It should be negative. What's the delta T of the water? So final minus initial. The initial of the cold water started at 20 and it went up to 23. Now remember, water gained it. So this should be a positive value. 23.6 minus 20, and I get 3.6 degrees. Okay? All right, so next calculation. Student claims that since the magnitude of delta T for the copper, so we're looking at delta T of copper, is greater, so we know the delta T of the copper is greater than the delta T of the water. It means that the magnitude of heat loss for copper is greater than the magnitude of the heat gained by water. Do you agree or disagree? When you're answering these type of questions, you first need to mention, do you agree or disagree? I disagree, I agree, and then why, okay? So remember, always answer the question and then why. So basically this question is stating this: is the magnitude, as in the value, of heat lost by copper less than, more than, or equal to the value of the heat gained by water. Well, there's something we need to remember. It's called the first law of thermodynamics. Okay? First law of thermodynamics states that energy cannot be created or destroyed. Okay? It can change from one form to another, which it did. The energy from the copper changed into the form of the energy gained by the water. Okay? Now, if we assume that the styrofoam cups are completely insulated, okay, as in closed system, aka constant pressure, okay, and that heat, and that no heat, let me fix that, and that no heat is lost to the surroundings. So the question is, now that you remember the first law of thermodynamics, energy cannot be created or destroyed. It can change from one form to another. But assuming that the cups are both insulated, closed system, pressure's not changing, and that no heat is lost to the surroundings, do you agree with their claim? Okay. The student claims that the temperature of the copper change is greater, so that means the magnitude of the heat is lost is greater than the magnitude of water. Disagree. Okay. I disagree with students' claim. Now, sometimes when you're in the moment of answering these types of questions, you can even mention this down here at the bottom too. You just have to mention it somewhere. I always like to put it in the beginning, okay? So that means that the magnitude of heat that was lost by copper has to equal the magnitude gained by the water. So in this case, just because temperature was different, was a bigger change for copper versus water, that doesn't mean that the heat values are going to be different. Because according to the law, whatever was lost by copper should be gained by the water. So I completely disagree with the student's claim. So let's actually calculate it, okay? So using the information given and the heat capacity equation, solve the specific heat of copper, okay? Well, we know water specific heat because we got to take water into account of this. We're going to use our specific heat equation to solve for copper because the heat lost by copper is also the heat gained by water. So if I use the equation and substitute that Q equals MC delta T, if I actually put it in that spot, I'm going to get Q right there, and I'm going to insert Q right there for the water. But one is negative and one is positive, okay? So this equation, when we solve for it, it's going to get pretty big. So we have the negative of the copper side. Well, we got to go back and look at our copper numbers. So for copper, the mass was 50. So I'm going to go back and forth on the page. It says, we are solving for specific heat. So we're going to call this little c. Multiply by delta T. Well, we already know what the delta T is because remember, we did this in part 1. So in part 1 or part A, we said negative 76.4. So we're going to say negative 76.4 degrees Celsius. Okay. So right here, That's what we're solving for. Okay, so I'm going to keep it highlighted so I can keep track of it. Okay, equals the gain. Okay, so I need the mass for water, which we said the mass of water was 100. Specific heat of water, 4.184 joules, grams, degrees Celsius. And then we need the delta T for water. So if we go up above, and remember we did this part in number 2. Actually, I'm going to call it, we did this in A. Oops, we did this in part A, and we did this in part B. So in part B, we said it was 3.6. Okay, so I'm going to tackle this side first because I have all the values. So I'm going to take 100 times 4.184 times 3.6. Okay, now my grams cancel, my degrees Celsius cancels, which is what I want. And I'm going to go off of 2 sig figs, so I got about 1,500 joules. Okay, now remember this is positive. I have over here, I have grams and degrees Celsius, and I have letter C, okay? So right here, I'm going to calculate my little c, but I'm going to bring this 50 down, and this 76, I'm going to bring it down here, okay? So this whole thing, we're going to bring down and divide. So I got negative 50 grams times negative 76.4. Okay. Well, take care of the denominator first. 50 times negative 76.4, you get, with 3 sig figs, you get negative 3820. Now, my units didn't cancel. I don't want them to cancel. But what's a negative times a negative? That negative and negative is going to become now positive. So now I'm going to take that 1,500 and I'm going to divide it by that 3820. And if we do this right, we should get that 0.39, which we do, 2 sig figs, 0.39 joules, grams, degrees Celsius. Okay? All right. And as I said, in lab, we will do that same thing also. Okay? In 6.1 to 6.5, I would like you to watch this video. As I said, highlight this title, go to around 30 minutes, watch it closely, take some notes. Now that we did one, now what if you did one yourself? So you're going to answer part A and B yourself, okay? You're going to continue watching, okay? The learning objectives, what if it's phase transitions? Because remember when we talked about in the beginning the learning objective, let me go back to it. There are 3 ways. Sorry, I got to go all the way to the back. Right here. Where'd it go? Right there. What if it's chemical? Okay. So heating and cooling, phase transitions, and then at the end of the notes right here, chemical reactions. So we just did heating and cooling, okay? So we're going to make a note of that. Okay, so right here, this is number 1, heating and cooling. Okay, number 2, you're going to continue watching the video around 30 minutes, okay? This is phase transitions. So number 2, how can phase transitions change heat being absorbed or released? Back in chapter 11, heating curves, what did we notice? Okay, which you need to watch the video and make some notes. Okay, notice right here on the y-axis is temperature, but on the x-axis is heat added. So right here, okay, as temperature increases, okay, we are still in the solid phase, okay? Because notice right here, this is a water. Water changes from a solid to a liquid at 0. So then we get the transition between solid and liquid. But we're not in the liquid stage yet. And then once we get to a certain point of time, then we're in the liquid stage. And then the liquid turning into liquid to gas, and I'm going to put equilibrium here. And then once we hit this 100 degrees, then we have this gas phase. But what did we mention in chapter 11? That as you are changing phase transitions, that heat is added, but no change in temperature. Look at that temperature. It's from 0, doesn't even change, but we still added heat. Same thing right here with liquid and gas. Even though I'm transitioning into a gas, my temperature is not changing. So as you boil that water, yes, you still have water, but you also have vapor coming off of it. Once you get to some point in time, okay, then you will have enough energy to take the rest of that water to change into a gas. So I'd like you to keep continuing watching that video, okay? Part 2, this is what happens. What if you actually have, number 3, a chemical reaction? So number 3, chemical reaction, okay? So what if it's a solution? What if you took a salt and added it to water, okay? Well, we know salts, if they're strong electrolytes, 100% dissociate. Well, you probably haven't thought of anything with this type of topic, but salts change temperature. You ever throw any salt in water as you're heating it up? I mean, why do you add salt to water besides taste? Well, you are trying to make those water molecules move faster. You're trying to break those intermolecular forces. You're trying to take that liquid into gas phase. You are trying to get that water to move more to create that energy to change to a liquid to a gas. So salt changes temperature. Whether it goes up or down, that depends on the salt. So each salt can either increase water's temperature or decrease water's temperature. Okay, so every salt is different. Okay, so as you watch this example of 45 minutes in the video, this was an AP type question where you'll see how it was part 2, a solution. Okay, beware of temperature. Okay, beware if it's exothermic. Okay, heat is lost. So if heat is lost, that means your Q is negative. If it's endothermic, then obviously your Q would be positive. So pay close attention. As temperature increases, your Q will decrease, which means your Q will go negative too. There's only 2 practice problems in our book where we actually have an actual sample to this, but we're going to do it in lab 2 in our practice textbook, number 55 and 56 in chapter 5. Okay? So finish that up, and if you get the right answer, you should get the following. I'll see you on the next one.